The topic of my talk is Introduction to the Molecular Dynamics Simulation, and it is in the FDP on computational techniques using HPC in physical sciences. So, as not only molecular dynamics, the high performance computing device, it is now a very useful drive in science, which works through the principle of simulation, and it has a huge application in today's industry. As you can see in the slide, that an environment to predict weather, to get the information about the pollution level, it works. Finding in the medical science, for finding the cures, basically for the drug designing, to see the protein folding or protein dynamics, it works very well. Also in the material science, specifically for the nanoscience, to get the detail about the structure dynamics, specifically in the application area of spinotronics, works very well. And also in the area of energy sciences, plasma sciences, fuel sciences, is a huge application nowadays. People are using high performance computing and the simulations in this area. Now, for today's part, which I will discuss actually, how I have used I have used this system or the molecular dynamics simulation basically for a specific topic, that is for the drug designing. So my emphasis will be towards in that way. But in the area of biomedical research, it has a huge application for the sequencing, for the brain modeling, for the getting the idea about detailed idea about the protein dynamics, system biology, and how you can see that the blood which will flow through the organ, the dynamics it will follow actually. We can get a detailed idea about the dynamics of that flow also, if we work with the this type of systems through the simulation, maybe Monte Carlo, it may be molecular dynamics simulation. Now, if we start to get an idea about the molecular dynamics, the story will start from the Schrodinger, because without Schrodinger equation, we cannot move a single step also. And we all know about the Schrodinger wave equation. If we want to solve the Schrodinger equation, if we want to establish the equation for a very basic system like the hydrogen atom, we can solve it very easily and in very small time. Its dimension is around 10 to the power minus 10 to the power minus 12 meter, and within a picosecond dynamics, it can solve the system very easily with the help of Schrodinger equation. But problem starts when the system is getting bigger, and if we move to the system of molecule, then the problem become a huge problem, because in those cases the Hamiltonian will be a issue, because when we write down the Hamiltonian, it will be a very complicated Hamiltonian, and in most of the cases, if the system is too large, for its atom also got large number of electron system, and for the molecular system, it is almost impossible to be solved. And if we want to solve the system also, the process will become too much expensive. So that is a very famous line of Dirac in 1929, that the underlying physical law necessary for the mathematical theory of large part of the physics and the whole of the chemistry are completely known. But the difficulty is to solve those equations, because in the most cases the problem is not solvable. So that means if we want to get a solution for those systems, to get the idea about the energy of that system or about the bond length, bond angle of that system, we need to apply some approximation. We have to apply some approximation techniques, which is applicable for the atomic and molecular system also. But in real world, we don't have only hydrogen atom. We have molecule, we have bigger molecule, and the molecular size is bigger and bigger in area. So there are many approximation molecular modeling techniques nowadays which are available to solve those systems theoretically. But if you can see that if the system dimension is very less, the accuracy level will be more. But if the system dimension is going to bigger and bigger, the accuracy level will become very less. And if you want to calculate those systems, you want to solve those systems to the simulation technique, that it will become very, very expensive. Now, if we can see in this case, there are many molecular modeling techniques which are available. Mainly quantum mechanics, basic quantum mechanics, Schrodinger equation we can apply in case of only hydrogen atom. But if we move to the hydrogen molecule, water molecule, Then slowly we have to move not only to the main quantum mechanics, but you have to move to the different molecular mechanics system where different approximation techniques are available to solve the system. And at the same time, if the dimension of the molecule is getting bigger and bigger, the time of solving those systems will be again getting bigger and bigger, which the basic idea you can get from this figure. It is this is the dimension for the two molecule system, and if the system is getting bigger, you can see that in this way the scenario will increase. So in the multi-level scale modeling system, we have the time is a specific issue here. If we want to solve the system in a very smaller molecular or atomic system, it will become very fast. We can solve it very easily. Up to, you can say that if the hydrogen atom in 10 to the power minus 15 femtosecond level, we can solve the system. So there are many methods which are known as ab initio methods. It applicable only for the smaller molecular system, where mainly Schrodinger equation is the main equation to solve this system. But if the molecular dimension is getting bigger, you can see that at the order of 10 to the power minus 8. In that case, ab initio method will fail, and in that case, we have to apply the other methods. In that scale, in the dimension of the molecular scale, there are many methods nowadays we apply for the molecular modeling system. There are ab initio, there are semi-empirical method, there are atomistic simulation method, there are mesoscale methods, and there are continuum model method also. Now we are interested, in my talk, I am interested only in this part, the molecular dynamics part, which is mainly lying in the area of atomistic simulation method. Now, if we want to discuss about little bit about the characteristics about the ab initio method, we can say that this type of system, we can to solve this type of system, we actually use Schrodinger equation, in which we as a specific characteristics, we can say that we generally handle with the bond length and bond angle of those system. For this system, actually, we can handle if we apply ab initio method, 10 to the power 2 to till atoms that we can apply the ab initio method to solve the system. In some cases, definitely we have to apply many approximation methods like Hattifok, WKB, or DFT. Nowadays, people are working on the DFT methods also. Next, if we go for the semi-empirical method, in this case, the system will get bigger, and in this case, the large electron system in the we generally apply. But for the semi-empirical method, the approximation is too much high. In this case, we only deal with the valence electron actually, and for that, the error in the calculation, there is a high chance of the error in the calculation, and exactly the difference between the exact result and the predicted result has some difference. Okay, mainly for the semi-empirical method, it applies for the molecules. But to solve this system, the time limit is more than that of the ab initio method. For the atomistic scale, where generally we apply the molecular simulation, actually in this case, we use some experimental data, and we take some ab initio theoretical data also. And here the basic parameter is the force field to create the equation. Now, in this case, the number of atoms generally we can handle, which is a large number of atom system, 10 to the power 6 atoms, till 10 to the power 6 atom, we can handle it easily. But the time scale for this type of system to solve it, it can go up to microsecond level. But in this case, the problem is that the accuracy level will be too much, not higher, it is lower, accuracy level is lower. Now, for the simulation of this type of system, the problem arises for the dynamic system, where the system can changes its parameter with time. The dynamics of many body system, actually, that is not it is not a, you can say that linear, but rather you can say that the dynamic is very chaotic in nature. And in for the dynamic system, the trajectories are very much complicated. If you can see the dynamics of the trajectory, you can say that the trajectory of the hurricane wave, you can see that the starting point of this wave may be the same, but after some time, the movement parameter, they changes with the time. So the very small differences in the starting condition, that creates or that lead to a exponential divergence in the outcome. So for this type of system, simulation is very difficult to get to get the detail about the system, how it is behaving with the time, and we cannot solve these systems very easily. Now, for the real life, actually the system, or you can say that our living cell, they behave like this uh, uh, dynamic system, and they are very much complex in nature. You can, for example, you can say that the proteins, the nucleic acid, protein folding, the ions, they are transported through the membranes, the enzymes which triggered the chemical reaction. The behavior of this type of system, they are actually very much complicated, and they are dynamic in nature. They changes their position, and their environment are too much complicated. Right? You can see that here. This is only a protein, and you can see that as a environment, there are huge water environment. How I can predict that it is a water environment? Because our body, where 95% is water only. So the when the protein is involved inside the body, how it is behaving, it depends on its environment also. So most of the biological system actually they are very much difficult to handle with, since they are dynamic, and they changes their position, their velocity, their acceleration with time. So due to this complexity of the biological systems, to get an idea about their characteristics, we need computational methods, and it is very important to get an insight about the life of the system. So that's why the molecular simulation came into the picture. Actually, it is what? It is the computational experiment it conducted on a molecular model, and many configuration in this case they are generics, and then we generally take the average on those configuration, which will be known as the measurement. For the molecular simulation, actually what we do, we take the help of theory also, we take the help of experiment also. So the simulation part will be done on both the parts, so it will get some input from the theory, and it will get some input from the experiment also. And it can applicable to the molecule, which ranging in the complexity from rare gases to polymers to metals and biological systems also. So number of molecule which can be handled to the molecular simulation process is too much large. Okay, there are many popular methods, but two popular methods which are very important for the molecular simulation part. I think one of the part already has been discussed with Professor Malik, that is the Monte Carlo simulation. And the next part which I am going to discuss with you today, that is the molecular dynamics part. Now the question arises, if it is dealing with the molecule, their bond length, bond angle, so why not to apply quantum mechanics? You can easily apply quantum mechanics, you can easily apply the Schrodinger equation. Yes, we can apply the Schrodinger equation, but to create the potential in this case, it will be very much difficult since the system is too much large, and it will be very hard to solve those problems, and it will be very much expensive to solve this problem. So what is the other alternative? And it will take a huge time to solve this type of big system. So the other alternative is to apply classical mechanics. And actually molecular dynamics deals with the classical mechanics. So where what we do, actually instead of using the quantum mechanics, in molecular simulation, we use normal classical Newtonian mechanics to model the probe system, the system which we want to know. It is a simplification of what is actually going on, and it is therefore less accurate. But we have to keep this in mind that it is not so accurate as the quantum mechanical result we get it from the Schrodinger equation. Now, in this case, what the help we generally take it from the quantum mechanics, some term we generally definitely get some constant term from the quantum mechanics, and which are going to be used for our molecular model in the molecular simulation. So, for this molecular model, what we need actually, we need the position of the system, we need the momentum, we need the charge, and also we need the information about the bond between the atoms or between the molecules. We need bond angle, we need dihedral angle, we need bond length. And the molecular model specifically here which generally we use, that is the very old model and very beautiful model which all of the physics people generally know, the variation between the potential energy and the separation. So we use basically this molecular model to get the interaction between the molecule, to get the detail about the interaction between the atoms. Okay, now so what is the molecular actual dynamics is? It is actually the study and the analyze of the dynamic nature of the system. The system may be a small atom, system may be a dynamic molecule undergoing chemical reaction, or system may be as large as a galaxy, which generally we can apply it for the protein system. And this, in this case, the modeling of the atomic or the molecular system, we use basic classical Newtonian mechanics system. So what are the equation normally we use? This is very old equation, the second law of motion of Newton, that is force is equal to mass into acceleration. where force can be described by del V del x minus negative potential of, and del V del x can be written as this equation. So all the three equations are very known to us. So we are going to use this equation to solve the system with varying time. That is actually the molecular dynamics simulation. It's a very robust and a valuable computer-based tool for studying the dynamic behavior. Now, in this case, dynamic behavior, what are the parameters we generally get? We get energies, we get the interactions of the biological system or the system under consideration. Mainly for the biological system, proteins, protein ligand interaction, nucleic acid, membrane, lipid, how they are moving, all the things can be discussed here. It gives us the time-dependent behavior of the complex system. Okay, for the molecular dynamics. Now, for the molecular dynamics, one of the parameter which is very much important, which from which generally we start the molecular dynamics, that is the force field. What is that force field? It is the expression which describes the dependence of energy of the system on the coordinate of the atoms. Actually, this thing we have to create for system, and it varies from system to system. And it actually is a set of equation, mainly the potential function, which used to generate the potential energy and their derivatives. And as a result of that, we can apply the force, we can derive the force. It consists an analytical form of the interatomic potential energy, which is a function of position, and a set of parameters which entering in that position. And here the parameters generally we obtain. So I have told you that for the molecular dynamics, we use some quantum mechanical data also from the theory, which we can get it from the ab initio calculation, and also we use some experimental data to fix this force field. So here the parameters generally we obtain it from the ab initio calculation, and also we get it from the experimental data. In the latter side, I will give you that information that which parameter we get from the ab initio calculation and which parameter generally we get it from the experimental data. Now, in this case, the molecules, the basic condition is that the molecules, they are defined as the collection of atoms, and we consider that they are held together by some elastic harmonic forces. That is the basic condition to create the force field of the molecular dynamics simulation. Now, when we create this type of force field, or to get the information about the potential, two parameters are very much important to keep in mind. One is the force due to the intramolecular interaction, and another one is the force due to intermolecular interaction. When the intramolecular interaction comes into play, in this case, we have to keep the points in mind, that is stretching, bending, and the dihedral and the motion which moves in a three dimension, that you have to keep in mind. And for the intermolecular force, mainly here we deals with the van der Waal interaction and Coulombic interaction. So when we calculate the potential for the system, we consider two types of bonding. One is the bonded interaction, which mainly comes from the intramolecular interaction, and another one is a non-bonded interaction, which comes mainly from the van der Waal interaction and the electrostatic interaction. Okay, so for van der Waal interaction, we are interested for non-modern interaction, we are interested in van der Waal and electrostatic. So one by one, I will little bit give you an idea about the what are the parameters, how we calculate the potential for van der Waal and the electrostatic case. Mainly for the van der Waal interaction, when we start the working with the molecular dynamics, we consider that as a whole the molecule has no electrical charge, but still the two molecules will come closer together, they will tend to attract together to form a closer system. So in this system, when they will come closer together, when the situation will come arise that overlapping of the electron cloud will take place, then we will say that after that there will be repulsion will come around. So van der Waal force will consider that part, and the potential or the electric field calculated for the van der Waal potential, it use a specific parameter for the molecular dynamics, that is the linear zones. So we generally van der Waal potential we write down in the term of linear zone potential, where this is the value where A and C are the it dependent on the system of or the atoms which you have in the inside the system, and basically this A and C parameter they came from the experimental data. For the electrostatic case, it is very known to us. We know that opposite charges attract and same charges repel. So for that, we use electrostatic force like this, and these are the very usual formula. By using this case, we can create the potential for the non-bonded case. Now, for the bonded case, it's also very important. For the bonded case, there are three type of interaction generally we consider to create the force field. One is the stretching along the bond, another one is the bending between the bonds, and third one is the rotation around the bonds. So let us take it one by one. Suppose you have a molecular system and you are getting the change in the bond length. So when the bond length will change, the potential will change. So by creating the variation of the bond length, where B naught is the initial bond length, where you can say that the system is not stretching, and B is the condition where the stretched part and the contraction part will appear. So by using this condition, we can create the force field, or we can create the field for the stretching case. Similarly, for the change in bond angle case, this is also a parameter where the bond angle will change and value of theta we can get. So in this case, the field is dependent on theta only. And the third one is the rotation of the bond. So this is actually the torsional potential, and the parameter here it depends on the phi. Now each of them can give their independent potential energy. So if we can see that only the diagonal angle, this is the torsional angle actually. If we can see that only the diagonal angle is changed, you can see that it gives its own potential energy. If the angle between two system bond in a bond length is changing, suppose the system has a single bond, or the system has a double bond, or the system has a triple bond. For each case, they give different potential energy term. So each and every component has its role to create the force field. So as a standard force field, when we consider create the force field, so we have to consider the change in bond length, we have to consider the change in bond angle, we have to consider the change in dihedral angle also. Similarly, we have to consider the van der Waal forces also. Similarly, we have to consider the Coulombic potential also. So for each and every term has its contribution to create the force field. So this is the basic parameter to create the force field of the system. Now there are many ways to calculate the force field in different systems, like the system which the molecular dynamics part which I am going to discuss here with you, that is the GROMACS, which is a free software. You can easily download it and you can easily run the software. So in that also there are many ways to calculate the force field. As you can see that this is the amber force field, GROMOS force field, OPLS force field. Yeah, I think yesterday there was a talk from IIT Delhi. Professor Diaz discussed about the OPLS force field. Today I am going to discuss with you about the GROMOS force field. So there are many force field. Different force field applies for the different type of system. Okay. Now when we create the field for the system, or the force field for the system, then the model building will be completed, and then the next part will be the simulation. Now for this computer simulation, what we do, we use uh, uh, second law of motion, and we vary the time for that equation, and we solve that equation. And by solving the equation, you can get the idea about the acceleration, velocity, position of the system, and which will give us the insight about the system. So this is the steps of the molecular simulation which we apply. But when we apply the molecular simulation, the molecular simulation in a single molecule cannot be simulated in the molecular simulation. When we have a single molecule, in surrounding that molecule, you have a huge number of environment, which applies for the biological system. So in real situation, as you can see, that it is a protein which is surrounded by many water molecules. So it is a reality that when you have a protein inside your body, inside your DNA, it is surrounded by many solvent molecules, basically water. So it is inside a sea of water. So to get and detail characteristics of this system, or the dynamics of this system, we need to solve the system to the molecular dynamics, where computer quantum mechanics cannot be operated. So we have to apply some classical atomistic approach to solve the equation. The basic equation we are going to solve it here, the Newton's equation. So what are the steps? So initially, when you are constructing a system, for the n-particle system, you should know about the mass, their position, their velocity, their acceleration. After that, you have to create the force field for the system. For that, you need the concept of the potential energy of the system. And when you have got the potential energy system, by easily you can apply the equation of motion, that means F is equal to m into a. For that, you will take the help of that potential. And after that, you have to solve the equation in this fixed time. Then we change the time of the system After some time, the velocity, the position of the system will change, and we in each time we solve that system and we get the result. So the scheme of the molecular dynamics is that first you have to set the particle in position, then you have to assign the system some velocities, then you have to calculate the force field, which is a very important parameter, then solve the system, then move the particle by a smaller time delta t, and you set the current position and the velocities, and in this way you again solve this system. So in this way, after certain time, after certain interval, you can calculate the system and you can stop your system. And when you stop the calculation, and you can analyze the data, how the system, the dynamic system is behaving. Now, how to set up the model, in what type of system we can apply the uh, molecular dynamics. As I told you that you can apply it for the atom, you can apply it from the molecule, and the molecular size uh, towards the size of galaxy, you can apply those systems. So to build the specimen, you can start your working with the unit cell also. You can start with the smaller dimension of the system, 1D system, 2D system, zero dimensional system also you can apply. Now, for this type of system, when we construct the system, we have to keep a point in mind that since the systems are too much big, so we have to apply some average in the system. And we have to keep in mind that how we are calculating. Normally, this type of calculation happens in room temperature. So, you have to fix the temperature of the system, and we have to fix the pressure of the system, you have to fix the volume of the system, you have to fix the energy of the system. So here the role plays for the different type of statistics. We can apply microcanonical ensemble, canonical ensemble, grand canonical ensemble. And another thing is that for the molecular dynamic system, mainly we apply Maxwell-Boltzmann statistics, and we apply it for the microcanonical ensemble. But one thing is very important here: what will be the boundary condition? When we construct the system, we have to specify that what will be the area, what will be the volume with which the particle will act. So you can apply the system like this. This you have to make the boundary like this, and you have to make a condition that if the system moves behind the boundary, then you will stop your calculation. So always boundary condition is very much effective. Otherwise, you cannot solve the equation, and the system will get distracted. Okay, so the cutoff region is very much important. As I can show you here, there are many number of molecules, and for the molecular dynamics, you can decide that step. That in every 10 step or in every 20 step, you will stop your calculation and you will see the boundary. If you have fixed a boundary, like in this case, I have created my probe system is 13, and I have considered that this will be the boundary of the system. So within this boundary, if the systems are remaining, then they will be considered for the molecular dynamics. The rest part will not be considered. So if the system probe system is 13, so the neighbor of this system is 8, 9, 16, 17, 15, 12, 10. So that you can decide how much in the boundary region you are choosing, and after which step you will stop your calculation. So if you are choosing a boundary, then the program will see that if after 10 step or after 20 step it is distributing, then it will discard this system. As you can see here, this part it is that it is distributed, and this part it is congested. So you have to choose that what will be your cutoff region for the molecular dynamics. Now, before going to the dynamics of the system, the preliminary step is to you have to minimize the system. It is not essential part. There are many calculations which have not minimized the system, but it is needed that you should minimize the system, because there are many systems, big systems, there are many local minimas. So to find the minimas, first of all, you have to optimize the system. This is the first part prior to the simulation process. Our goal is to find the optimization of the system. As you can see here, this I have shown you like one of the part. This is a interaction between a protein and a drug. So I have to check that when the interaction is going on, if there is no drug, so protein is a stable protein or not, and if the protein is interacted with the drug, then the complex they are forming, that is also stable or not. So this is the first step. So after getting minimization, you can move to the next step. For minimization, there are many ways to apply to check the minimization. Steepest descent is one of the process. Newton reaction is another of the process. Mainly for the molecular dynamics in the GROMACS, we use Newton reaction method to go for the minimization process. Now, after doing the minimization, first set of data will come. That After minimization, the system will generally give us the normal mode analysis from where we can get the stretching, bending, and stretching bending mode information. So these are the characteristic information which we can get after the minimization of the system, when the potential will go to the minimum. And then when we apply the force field in the system, I have told you that some experimental data also we get. Now what are those experimental data? Actually the experimental data we get it from the X-ray or Newton scattering of the crystal structure. Basically when we do the simulation for the protein structure, we get the protein structure and the information of protein structure. In that case we generally use the X-ray data of the protein structure, that is crystallographic data. In some cases we get some infrared information also, and in some cases we get some NMR information also. And from the ab initio result, basically we get the information of the dihedral angle change. Information we generally get it from the dihedral angles, which is due to the minimization process we can get the information. Then basically since the system we get the energy minimization, after that the system should be equilibrated. Means we have system should be placed under the huge number of water system. You have to decide the structure. When the system will be inside the water system, the system should come at the equilibrium. So to come at the equilibrium, we have to apply some statistical techniques, and mainly for the molecular dynamics part, we apply microcanonical techniques where N, V, E are fixed, and for that there are many techniques, NVT, NPT. We can apply all the techniques. It depends on you what type of statistics you want to apply for your calculation, and the system will get equilibrated. That means the system should operate at a fixed temperature. That temperature also we can fix. But in GROMACS, molecular dynamics, we generally apply it, I think 313 or 315 pk and 1 bar for the pressure. Then the next part is the time integration scheme, because I have told you that we have to solve the Newton's equation with by some fixed time interval. So these are the discretization in the time. For that we generally apply the Taylor expansion, and we have to apply it to some get it the summing, and for that a specific algorithm normally we apply for the molecular dynamics, that is Bartlett central difference algorithm. So when we apply the system and we move the system with time, as you can see in this animation, you can see that after certain time the system will get stable. That is actually our requirement. So for that we can start the calculation for 1 nanosecond, we can do the calculation for 10 nanosecond, we can do the calculation for 100 nanosecond, we can do the calculation for 200 nanosecond, 500 nanosecond. It depends on your system how when it will get stabilized. So what is the protocol for the MD simulation? First you have to create the initial coordinate of the system, that you can get from the structure biology data. For the protein and ligand interaction, for the drug designing, mainly protein data we can get it from the PDB bank, and the drug data we can get from PubChem. Then we have to do the minimization of the structure. Then you have to apply some initial velocities. For that I have told you that we generally apply Maxwell-Boltzmann statistics. Then we have to slowly increase the heating of the dynamics. That means we have to give some desired temperature. It cannot go 0 degree absolute. So we apply it for the room temperature, because for the drug designing, the system should work at the room temperature. Then we have to equilibrate the system, and the system is ready for the molecular dynamics. Then we will solve the Newtonian equation with some steps of time, and after that running the system we can analyze the trajectories, how the system is behaving. Now when the system is equally equilibrated, it is equilibrated or not, that also you can see step by step. As you can say that here I have calculated the temperature with some steps, and here after 5000 steps you can see that till 5000 steps mostly the system is equilibrated, and it is equilibrated I think after 10 or 15 steps. So with the temperature, this is equilibrated, so your system is ready for the molecular dynamics. Similarly, we can get the information about the pressure, we can get the information about the energy, total energy, potential energy, all. There are many softwares to deal with the MD simulation which are available in market, and there are 5 mostly common used softwares which are available in the market. They are GROMACS, CHARM, AMBER, NAMD, LAMMPS. Some of these softwares they are free, or you can say that open source, mainly GROMACS and LAMMPS. But the rest softwares, CHARM, AMBER, LAM, you have to buy it commercially. Also, there are some other software which are also available. Some of the softwares which are Linux based, and there are some software which are Windows based also. Like Desmond, you can buy it, but it's very costly. For the biological application, mainly GROMACS, NAMD, and AMBER systems seems to prove them very suitable. For the material analysis, LAMMPS is a very good tool to analyze the material system. And the GROMACS actually, since I have worked with GROMACS, since it is free, it is Linux-based system. For it, you generally use Bash shell scripting and the Python 3 programming language. It is necessary to run this GROMACS system. There are various Python laboratories which are also available nowadays in the market. They are NumPy, Pandas, Pipi for the data manipulation and the numerical and the scientific calculation. There are many softwares also which are used for the graphical plot, and the data you are getting after that you need the graphical plots and figures. So for that there are many things. You can get the data from the data set also. You can fit it in the Excel and the origin also to get the detail about the graphical information. There are many software to deal with the structures. For structures, PyMol, Image Magic, Gauss View, these are very popularly used softwares which are used to deal with the structures and after the calculation to create the simulation movies also. And XMGRACE is used to for the graph plotting and the conversion of the data. This is very important. Now the question arises, where is the high performance computing takes place here? Now for MD simulation part, since I have told you the system is too much big, environment is too much big here, so it needs some parallel computation to get a result after a desirable time. Otherwise, if you want to solve it and you want to use it, your calculation in a single system, it will take 2 months, 3 months time to solve a single system. But if you need a urgent result, fast result, you need the computation should be in a parallel way. So for every step in this case, for each system or for the each atom, is the first condition is that it must be within the cutoff radius, and we need a good simulator system or parallel system to work with. So for that, when we apply the parallel system, actually what we do, the whole system will be divided into some blocks, as you can see here, the upper part and the lower part. So it will divide into some boxes. Each boxes will be known as nodes, and each node will handle a different bonded interaction within that cutoff area. So suppose I am considering a box or node like this. So this node will handle only the molecules in this area. If I am interested in this node, so this node will only handle the interaction in this area. Here the role of HPC plays. So in our institute, we have Ramanujam Universe, which is the high performance computing system, which is powered by Dell Technologies and the Gene Information Technologies. But we have in our HPC system, we have 6 computer nodes, 2 input output nodes, and 1 master node in the cluster. In total, we have 576 cores comprising of 384 core of computing nodes. So each node can be accessible in that case. We have 4.5 terabyte RAM and 500 terabyte usable storage. We have 8 into A100 NVIDIA GPU cards for the accelerator node. Now the 6 component nodes which creates the processing very faster. And these 576 cores, they have the ability to work on multiple projects simultaneously and efficiently. So only one work will not be applicable. So multiple people can put their work parallelly in different nodes. And since we have 4.5 terabyte RAM and TB RAM, so which projects with a lot of data can be dealt with at a same time. And since we have a GPU cards also with the accelerator node, which have the ability to utilize the graphical processing also. So we can, at the same time, we can get the graphical processing also. Now the question is, if number of CPU, number of cores are more, then how fast the calculation it is. So for a GROMACS system, I can easily show you, if the number of CPU is more, the nanoseconds per day will be less. So if the core is more, you can say that the timing will be very less to run a system. So that is the requirement of the large number of cores. Now for the work, if you get an output and you have stopped the MD simulation, now you are getting some trajectory analysis. What type of analysis you can do? You can get the idea about the root mean square deviation of the system with time. You can get the idea about the root mean square fluctuation of the system. You can get the information about radius of gyration. You can get the idea about the solvent accessible solvent area, whole about the system. The information about the hydrogen bonding between your system and the environment. You can get the idea about the PC analysis, secondary structure analysis. You can get the simulation movie of also how it is behaving with time. You can get the kernel density, interaction, hydrogen bonding matrix. You can get the molecular mechanics, that means the binding energy, free energy of the system, every information from the output of the trajectory you can get. So all these analysis will give us the valuable information regarding the stability, folding, conformational changes, interaction, dynamics of your fluid system in environment, system as an individual also. Now, what the thing for my work, what I have done, I have started working. I have told you that in the COVID time. So at that time, I was interested with the drug of the COVID. There was no known drug for the drug of the COVID. So I have started my work with some um, medicinal plants. And one of the medicinal plants at that time, already we India, we use many medicinal plants like giloy, like tulsi. We use that. So one of the in my work, I have used giloy as a medicinal plant. I get some information about the phytoconstituents on that medicinal plant. I have so and check that they are very much good effect on the some viral infection. So this is the protein for that viral virus of COVID. This is actually SARS CoV-2 protein, and this is the ligand which I got it from the giloy plant. And I have to check that is it interacting with the protein. If it wants to act as a drug, so it should target the drug. It should interact with the protein. It's interact with the virus. Then only it can act on the virus. So this is that interaction. When it will interact with the protein, it will go inside the protein. It will bind with the protein. Every interaction had to happen. That information you can easily get from the molecular dynamics. So here you can see that berberine is one of the phytoconstituent of this actually giloy plant. Okay, so this is the protein also actually the virus, which is already the structure is already available in many software. That PDB is one of the protein data bank is one of the structure where we can get the crystal structure, extra information about this protein structure, and we have to check that the protein is interacting with the drug or not. If protein is interacting with the drug, then both the complexation between drug and protein will interact and they will come closer by. So RMS is the information which can give average distance between the atoms of the protein and between the atoms of the drug. So this is one information you can get. Similarly, RMSF. RMSF is that fluctuation, how much distance it is creating between the protein and the drug. So this information also you can get it from the RMSA value from the molecular dynamics. Here you can see that in this case, the drug is going inside the protein, and when it is going inside the protein, it is interacting inside the interacting protein. Then we can calculate the interaction energy. As you can see that the interaction energy is coming out as minus 5.1 kilocalorie per mole. So if it will not interact with the protein, then it will not go inside the protein. It will come outside. So that information, when you will get a trajectory which is time dependent, it will be easier to see that it is going inside the protein or not. This type of work can be done. So this is the another picture. You can see that when I have started the calculation at 0 picosecond, this is the position of the drug inside the protein. And now after 50,000 picosecond, when I have done the calculation, the structure of the drug is same, but only it has been rotated. It didn't came out of the protein or didn't go inside the protein, but only it has been rotated. So this type of information very easily, how the dynamics of the system is moving inside the system, you can easily get that information from the molecular dynamic simulation. This is another work which we have done during that COVID time also. As all you know that at that time, since till now we don't have any drug for the COVID, but there are many repurposed drug we have used for the COVID treatment. And one of the very popular repurposed drug was favipiravir. Another popular drug was hydroxychloroquine. All of us know that. Later on, it has been discarded. Oseltamivir. These are all repurposed drugs. So what we have done, we have checked the interaction parameter or the energy of interaction when they are interacting with the COVID virus protein. So these are the parameters, these are the information. If they are working alone is a good, or when they are working is as a combined form, it is good. That type of information also you can get from the molecular dynamic simulation data. So in this case, as you can see that when favipiravir individually is working, the interaction energy is minus 4.4 kilocalorie. When hydroxychloroquine individually is working, it is minus 4.8 kilocalorie. But whereas oseltamivir is interacting, its energy is too much lower. So this is finally binding with the COVID protein. And then what we have done, we have repurposed the drug in a combination mode. As you can see that this is the first one, this is the second one combination mode, and all the three drugs are inside. So you can see that oseltamivir as a individual drug, it is acting very beautifully with the COVID protein. So this type of simulation study, this type of result, before going to the experimental study, it generally help us to decide that which drug is acting properly or not. Not only that, we can get the idea about the free energy calculation of the system also. We can say that how the solute is going inside the solvent, or we are getting a good solution or not. That also information you can get from the molecular dynamic calculation. And also there are many studies are going on, which gives us a time dependent variation. As you can see that this is a very nano sized system, how it is behaving with the lipid layer. It is interacting, since it is a drug relatively, and it is trying to interact with the lipid layer. As you can see that from 0 nanosecond the calculation has been started, the simulation. After 114 nanosecond it is attached. At 115 nanosecond it is going to trying to go inside. In 116 nanosecond again it is trying to go inside, and after 2000 nanosecond it is totally trapped by the lipid layer inside the body. So this type of information, easily we can get that how the molecule is interacting with the environment. The environment may be water medium, environment may be lipid, environment may be bilayer of the protein. All the information can get it from the molecular dynamics simulation. So I have worked on this from quite 2 3 years. So these are some publications which I have published from the MD simulation, basically by using the GROMACS, which is a very free software, and it's a easily available software and works in a Linux system, so anybody can work in that system. So these are my group members, and thank you for joining me and hearing.